Hello everyone. In this video, we shall see regression analysis. In correlation, we had seen that correlation analysis helps us to check whether are the two variables correlated or not, and if yes, how is the correlation, strong or weak. But correlation analysis does not measure the amount of relationship between the two variables. Regression helps us to do that. Regression is defined as the measure of average relationship between two or more variables. While correlation attempts to study the relationship between two variables, regression analysis attempts to predict the average value of one variable given the value of the other variable. Sir Francis Galton, a British biometrician, defined regression as stepping back towards the average. While studying, he found that offsprings of abnormally tall or short parents are of average height. They tend to regress or step back to the average values. They are not abnormally tall or short. Thus, regression attempts to quantify the dependence of one variable on the other. For two variables x and y, when y depends on x, the dependence is expressed in form of a linear equation y is equal to a plus bx, equation of a straight line. This regression equation is used to estimate the values of the dependent variables for the given values of the independent variables. It also measures the error involved while using the regression line as a basis of estimation. In correlation, we had seen scatter plot where the two variables were plotted on the two axes and the points or the observations were plotted on the graph. If a straight line can be drawn through the points of a scatter diagram, it is called as the line of regression. Unless the correlation is perfect, all the points will not lie on the straight line or the line of regression. There will be few points away from the line, below the line or above the line, and the difference of each point from the line or the distance of each point from the line is called as an error. If you look at this diagram, you can see that there are points above the line as well as below the line. Now, when I say that I can find out the distance or the difference of every point from the line and minimize it, the distance can be measured in two ways. It can either be parallel to x-axis for a particular point, or it can be parallel to y-axis. If I try to collect the distance of all the points parallel to x-axis and try to minimize the error, I get regression equation of one type, and for the other I get regression equation of the other type. Hence, there are two regression lines, a line of regression of y on x and of x on y. Smaller the angle between these regression lines, the higher will be the correlation between the two variables. Let us have a look on regression line of y on x. This is represented by the equation y is equal to a plus bx. Here x is called as the independent variable and y is called as the dependent variable. It can be clearly seen from the equation that y depends on x. Now, if we try to minimize the errors of all the points which do not lie on the line, while doing so, we get two normal equations when we differentiate the error with respect to two constants a and b. These are the normal equations. When we solve these two equations in two unknowns a and b, we will get a and b in form of the following formulae. These are the formulae with the help of which a and b can be estimated. Similarly, we will use these values in the regression equation of y on x. It can either be written as y equal to a plus bx or y minus y bar equal to byx equal into x minus x bar, where byx is nothing but regression coefficient of y on x. This value b is the regression coefficient and a is the intercept of the line. Similar logic can be applied for regression equation of x on y. The equations are given as x equal to a dash plus b dash y. In this case, y is the independent variable and x is the dependent variable. Same situation if we try to minimize the error. By differentiating with respect to a dash and b dash, we get two normal equations, 1 and 2, and these are two equations in two unknowns a dash and b dash, and when we try to solve them simultaneously, we get the estimated values of a dash and b dash, where b dash is also called as bxy, regression coefficient of x on y. And the same logic for obtaining the regression equations by substituting the values of a dash and b dash or x bar and y bar along with bx, y or b dash. Let us see a few properties of regression coefficients. Regression coefficients represent the slope of the respective lines of regression. The point of intersection of these two regression lines is the mean of the two variables. A regression coefficient represents the increment in the value of the dependent variable corresponding to a unit change in the value of the independent variable. If one of the values is negative, the other value is also negative. That is, if byx is negative, bxy is also negative, and so is r. So byx, bxy and r are all three positive or all three negative. There also exists a relationship between the two. That is, if you take the product of byx into bxy, the resultant is equal to the square of the correlation coefficient r. Moreover, r is the square root of this product. But since both byx and bxy will be either positive or both will be negative, the sign of r will depend on the sign of the regression coefficients. Though the product byx into bxy is always positive, if they are negative, each of them is negative, r will also be negative.